Welcome. Let's continue looking at our rocket launch. Now recall that our rocket has been launched and it is rising vertically, and that we have a camera located 5,000 feet from the launch pad. And so we had created a diagram looking something like this, where we have this right triangle where the rocket is at one vertex, the camera is at another vertex, and the launch pad is at the third vertex. And we know that this is a constant 5,000 feet, but we know that the rocket is rising. So this height or altitude of the triangle and of the rocket is something that's changing over time. It's not a constant value. So we had labeled that as h. Now in this new question, we want to find the velocity of the rocket. If the height of the rocket is 2,000 feet and the camera's angle is changing at a rate of 0.12 radians per second. So notice it mentions the camera's angle, and so we had identified the camera's angle as theta in that location at the vertex containing the camera. And so let's translate what we're being asked to do here into mathematical notation. So first of all, we want to find the velocity of the rocket. Well, the velocity of the rocket is how fast this rocket is rising. So the velocity of the rocket is Dhdt, because h is what's measuring the height of the rocket. So it's measuring the position of the rocket. So we want to find Dhdt under certain conditions. And the conditions we're interested in is when the rocket is 2,000 feet high. So we want to find Dhdt when h is 2,000 feet and when the camera's angle is changing at a rate. So we have a rate of change in the angle. So, and our rate of change for our angle theta needs to be 0.12 radians per second. Okay, so we need to start with an equation that relates the height of the rocket with the angle of the camera, so that when we apply our derivative to the equation, we can relate the rate of change of the height to the rate of change of the angle. So we previously saw that it was helpful, given the information we have in our diagram, that one side is h, the side opposite the angle is h, and the side adjacent is 5,000. It was advantageous to look at the tangent function. Specifically, that the tangent of angle theta is h over 5,000. And now, with that equation, if we apply the derivative with respect to time on both sides of that equation, we will end up with an equation that indeed relates the rate of change of the height of the rocket to the rate of change of the angle of the camera. So let's go ahead and apply the derivative with respect to time on both sides of this equation. And in doing so, we end up with secant squared of theta d theta dt equals 1 over 5,000 dh dt. Now, if that 1 over 5,000 dh dt is not perfectly obvious to you, note that h over 5,000 is the same as saying 1 over 5,000 times h. Okay, so anyway, what we need now is to look back at what we decided we were trying to do, and we were trying to find Dht. So in my equation relating the rates of height and theta angle, here is my Dht. That is what I wish to find. So solving for Dht, I simply need to multiply both sides of this equation by 5,000. So let's go ahead and do that. And when I multiply both sides of the equation by 5,000, I end up with Dht equaling 5,000 times secant squared of theta times d theta dt. Now, at this point, I need to take an inventory of what I know and what I don't know in this equation about Dht. 5,000 is a constant. We're good there. Notice that we were already given information about d theta dt, so we can replace that information rather easily into our equation. But we need to determine what is secant squared of theta. Now, recall that secant of theta is typically represented as hypotenuse over adjacent. And that's because secant of theta is the reciprocal of cosine of theta. So to determine what secant theta is and then square it, we need to know the ratio of hypotenuse to the side adjacent. Well, the side adjacent is easy. That is always 5,000 feet because the camera is always 5,000 feet from the launch pad. However, we need to find the hypotenuse, and while that is not given to me, we do have sufficient information to determine that. Notice we were told that the height of the rocket we're interested in is 2,000 feet. So I'm going to update my diagram to represent the fact that now we are interested in a specific snapshot in time. And the specific snapshot in time that I'm interested in is when that height is 2,000 feet. And with the information about the height and the base of this triangle, we can go ahead and find that hypotenuse. So we'll call that S, and we'll go ahead and determine the value of S. So this numerator in my secant ratio will be S, and let's figure out what that is. So because it's a right triangle, we can use the Pythagorean theorem, and because we're looking at a length of a side, we're not going to include plus or minus. Simply we want the positive root from the Pythagorean theorem. So we'll have S is equal to 2,000 squared plus 5,000 squared. And so we can simplify this quantity in the square root to be 1,000 times the square root of 29. So updating my diagram here as 1,000 times the square root of 29, that means that my secant ratio is equal to 1,000 times the square root of 29. And notice that the 1,000 and the 5,000 can be simplified to 1/5 by dividing both by 1,000. So our secant ratio is equal to the square root of 29 over 5. So let's go ahead and insert our information into our equation that's relating the rates of height and theta. So we end up with Dhdt is equal to 5,000 times the square root of 29 over 5 squared times 0.12. Now, let's expand that a little bit. We'll get 5,000 times, now the square root of 29 squared will just give us a 29, over 25, 5 squared is 25, and then we need to multiply that by 0.12. So then Dhdt is equal to, so we can simplify the 25 going into 5,000 to make our life a little easier. 25 goes into 5,000 25 times. And then we can multiply the 25 and the 29, and we get 5,800. And then we need to multiply that by the 0.12. And when we do that, we end up with 696. And our height, our Dhdt is measured in feet per second. So now what's left to do is to interpret our work within the context of the problem. And so as we interpret our results, what we can say is that given that a camera 5,000 feet from the launch pad must rotate at a rate of 0.12 radians per second when the rocket is 2,000 feet above the launch pad, the velocity of that rocket is 696 feet per second. I hope this was helpful.